Hello and welcome to lesson 22. Today we are looking at a special type of differentiation, which is our implicit differentiation. So we're going to be learning a technique that is going to help us with specific functions. So let's start with an example. You may be familiar with this equation here, which is the equation of a circle, and specifically it'll be a circle with that will look like this. Oh, maybe a little bit better, with the origin as the center of the circle. And so it has a radius of 1, and yes, it is centered at the origin. So to find the derivative of this equation with respect to x, and this is very important here, we are going to start by differentiating both sides. As you can see, it's hard to find what y is right away, or maybe we just don't want to move around or change or rearrange our equation, and we just want to find the derivative as is. So we will have on the left-hand side the derivative of x squared plus y squared, and on the right-hand side, we just have the derivative of 1, which is equal to 0. Now for the left-hand side, we are going to first apply the sum rule because we have two terms that are being added together. So in the first term, we have d of x squared by dx, and in the second term, we have d of y squared by d of x. Okay, now the first term, this is just our power rule, so we get 2x. But in this part, this is now a composite function. We actually have the function x squared, but now our inner function is y. And we don't know necessarily what y is. We are just treating it as a function. So that's why when we differentiate, we have 2y, which comes from the power rule. And then from the chain rule, we have the derivative of the inner function, which is y by d of x. So dy by d of x. And this was what we were trying to find when we were trying to differentiate over here. So we were really looking for dy by dx from the start. And now we have this in our expression here. So all we have now to do to find this is to rearrange and solve for that term. So in the right-hand side, I'm going to have negative 2x and then divide by 2y. And simplifying this, this is just equal to negative x over y. And just for yourself to double check, if you start here, y squared 1 minus x squared. So you'll see this will be a little bit more complex to solve. And so that's why we sometimes need implicit differentiation to help us solve the derivative of certain functions. So now just as a test to see if you understood what we just did, try to find exactly as I did the derivative of dy by dx for x times y is equal to 1. And I will take it up momentarily, but just if you're trying it, this is a product and you can apply the product rule. So now let's try it together. So similar to above, we're going to differentiate both sides. So I will have on the left-hand side d of xy by d of x, and on the right-hand side d of 1 by dx, which again, this is equal to 0. Now, on the left-hand side, we are going to apply the product rule, and the product rule tells me I find the derivative of x times y, and then x times the derivative of y. So, because this is the derivative with respect to x, this first term is just 1, and so it is 1 times y, which is just y. Now, in the second term, d of y by d of x is the term we were looking for, which is dy by dx. And then I just have that x as being multiplied here as well. So now we are trying to find for that derivative, so we rearrange. So I'll move negative y over, and then divide by x on both sides. So then I have negative y over x, but we're just going to substitute the value of y here, which from xy is equal to 1, y is 1 over x. And so we have now negative 1 over x squared. And if you already didn't make this connection, I hope you can see that based on this value that I found here, which is just a rearranging of the function, then y prime of x using our power rules or sorry, let me write it this way. Y would be x negative 1, and then using our power rules, and just what we've seen in our lesson so far, this is negative 1 over x squared, which is exactly what we found here, just using a different approach. Now, before I jump into some other examples, which are going to help you see why we are learning implicit differentiation, let's get some definitions here. So starting with an explicit relation, it's a relationship or a function where y or f of x is an expression of x. So our input variable x or our independent variable x, and then our output is just expression using x. So we can actually directly calculate y by knowing what x is. We just substitute and we have our output for y. And the functions you've worked with so far are explicit functions. Now we have an idea of implicit relations. And consider now that these are relations and they are not necessarily functions. Because think of the example we saw above as well with the circle. If we have this circle here, then based on the vertical line test for functions, you can see that the vertical line is passing through 2 points at many different values of x. So this is not a function, but it is a relation still because we are making a connection between x and y. So it is an implicit relation is a relationship that has an implicit equation, and it could have more than two variables, but we're mostly going to be seeing x and y. But one variable is not defined explicitly as the other, such as here. We can see that we have x squared plus y squared. So if I have a value of x direct, like any input value of x, I can't directly find what y is. And I may have to do a little bit more work to find what my y value could be. And you can see that for different values of x, there could be more than one y value. And that's exactly what we were showing above when we did y squared is equal to 1 minus x squared. Because taking the square root here, you do have that plus or minus sign. And so you actually have two different values of y there. And if you were to find the derivative of this itself, you have to split it into a splitwise function and look at it in two different ways. And again, that would be a little bit too complex and not really what we're doing in this course. And now we've seen that using implicit differentiation, which is the process we did up in example 1 and 2, that we were able to find this derivative in a much simpler way. So now, just giving you an algorithm for that, for implicit differentiation. So it is a method of finding the derivative of an implicit relation, and we actually use chain rule. So we differentiate both sides of our function with respect to x, and that's the same as saying we differentiate with respect to x because that's already implied that you're differentiating the whole equation, and that would mean both left-hand and right-hand side. And when doing that, you definitely have one y somewhere in your function. So then using chain rule, you're going to end up with dy by dx somewhere in your differentiation. So then you're going to isolate all those terms together and factor so you have just dy by dx on one side because our goal is to isolate for that term. So we have found the derivative or y prime. And finally, we solve for dy by dx or our y prime, which is our goal to begin with. So now, the two examples, and actually maybe in this example you can see it already, but in the other example, we didn't really need to do implicit differentiation. So I want you to think, when might implicit differentiation be useful? And specifically think of different types of implicit relations that we can see, or different equations that are implicit equations, and implicit differentiation may be helpful for us. So in our first example here, we are going to actually need implicit differentiation. Here we have x squared plus xy plus y cubed, and so we are not able to solve for y, and especially because y is appearing in more than one term. So we will take the derivative of both sides with respect to x. And so using the sum rule, we're just taking the derivative of each of the three terms. And on this side, we did actually do d of 0 by dx, but this is just 0. So you don't need to write that at this point. If you just write 0, you are showing that you understand the derivative of a constant. Now, for each of these three terms, we are applying a combination of power rule, product rule, and chain rule to get the following. So in the first one, x squared, we're differentiating with respect to x, so we can just apply the power rule. We have 2x. But in the second term, we have x times y, and we have seen this one solved before as well. But this is now our product rule, so we get dx by dx times y and x times dy by dx. So already we have one of these that we need. Now in the second term, y cubed, this is a composite function. So it's the cubic function with our inner function as y. So we will do the chain rule here. So our outer function as a power rule is just 3y squared, and the derivative of the inner function, so dy by dx. And again, we have that term that we want. So now I will factor the coefficients, or I will factor out dy by dx, and I'll be left with x plus 3y squared, which is what we see right here. And now I am solving for this term, which is our derivative. So again, this is y prime. And so these two, I can just move over to the left-hand side, and I'll get negative 2x negative y. And then I'm dividing by this bracket here, so x plus 3y squared. And so I have found what my derivative dy by dx will be. Now, previous lesson, I mentioned that we don't want our derivative to be an expression with both x and y, but in this lesson, because we are working with more complex functions, so as you can see right here, it's harder to find what y would be. And in some cases, maybe beyond your skills to find a simple equation for y. So for this lesson, and when we are doing implicit differentiation, you can actually keep your derivative as an expression of both x and y, so have two variables in there, and that will be fine. So our work here would be done, and that's our derivative. And again, I hope you can see you weren't able to find the derivative here using any other methods that you've seen so far, but implicit differentiation actually gives us a very simple way of solving for the derivative. Now let's try another example. And in this case, we do have a similar function, but we are finding the equation of the tangent at a specific point. So let's start by taking the derivative of both sides because we want to find y prime. And y prime is going to give us that value of m, which is the slope of our tangent. So similar to above, I first take the sum rule to find the derivative of each of those individual terms. And again, here I have a 4, but I did write it just so you see, but this would also be 0. So again, if you just write 0, I'll understand that you know that this is the derivative of the constant. And now we have our power rule, which gives us 6x squared for this term here. Then this term is our product rule because we have x squared times y, so we find the derivative of each of those terms and then add them together. And then here we have that chain rule again. So we have the power rule, so 2y, and then we find dy by dx. So again, we want that dy by dx. So I will factor out, so I will have, perfect, I wrote it there for you. If we factor out that dy by dx, I am left with x squared plus 2y. And my first two terms I just leave as is for now. And we are solving for dy by dx, so I'm just going to do a bit of rearranging now. So these two terms are now moved to the other side, so they're negative 6x squared minus 2xy, and we divide by that bracket there, x squared plus 2y. So then this is my derivative. And now I have my point, which was negative 1, 2. There, given our point negative 1, 2, we have what x is. X is just negative 1. And we have what y is. Y is just 2. So we can actually use just this expression here and use substitution to find what our the slope of our tangent, or dy dx, and this is at x is equal to negative 1 would be. So inputting those values and evaluating, we end up with negative 2 over 5. So this is our slope m. And we already had the point, so negative 1 and 2, we don't have to do any further evaluation. So we can solve for b here. And again, this is just substitution of y equals mx plus b. And we find that b will be 8 over 5. And so the equation of the tangent to the curve at that point is given by y equals negative 2 over 5x plus 8 over 5. And so if we graph this, you will see, and I hope you can see this is a very strange shape, but still it is a relation nonetheless. And we can see that at that point, the equation of the line that we found is the tangent to the function at that specific point. And again, we were able to use implicit differentiation to be able to solve this. Now, one thing I want to point out here is that had you been given just the value of x, again, it would be hard to find what y is, and that's why you were given the point with both x and y given to you, so then you are just able to do substitution. And again, we found our equation of the line pretty simply. Now let's look at implicit differentiation with exponential relations. Start by taking the derivative of both sides. So in this, in the left-hand side, I have a product rule, and then in the right-hand side, I have a sum rule. So in my left-hand side, I take the derivative of y squared, and then times just the other product, so e to the power of 2x. And then here we have y squared, and then times the derivative of e to the power of 2x. And then on my right-hand side, I take the derivative, and this is just a sum rule. So the derivative of 4y by dx and the derivative of x squared by dx. Now, keep in mind again, this part, so here, and actually here, we have the chain rule because y is our inner function. So this is your quadratic function, and this is just a linear line, but with y as our inner function. So when differentiating, we do use the chain rule. So here using power rule, I have 2y, and then I have to differentiate with respect to x, so dy by dx. And this is now that term we're looking for. And the e to the power 2x, I just keep, it just was being multiplied there, so it stays there. And here, I actually have a chain rule as well because we have e to the power 2x. So we do have that e to the power 2x based on the derivative of exponential functions, and then the derivative of the exponent itself. So d of 2x by d of x is just 2. So that's why we have that 2 there as well. And then for this part, this is the constant multiple rule. So I just take factor 4 out, and then I'm left with dy by dx, which is, again, the term we're looking for. Now, this one looks a little bit different than the ones we've worked on so far because you have dy by dx both in the left-hand side and the right-hand side. And now we actually see that isolating part come into play. So we are going to isolate both of the terms with dy by dx, and all the other terms are now on the other side. Now, if I factor out dy by dx, I am left with, as you can see, 2y and then e2 to the power of x, and then this negative 4 here. And that's exactly what you see here, which is if I had shown you the factoring step, but I just skipped it here because you've seen it several times now, then your final derivative is equal to this expression, which again, this is the numerator here, and these terms give you the denominator that was factored out. And yeah, that's our final derivative for this question. And then we're going to see now an implicit differentiation with trigonometric relations. So given the function x is equal to sine of y, we see that y is now our input value for the sine function. This is actually the inverse of the sine function of y is equal to sine of -1 or to the power of -1 of x. And it is equal to the function that we want. So you can use trigonometric properties here as well, but I'm just going to show you with implicit differentiation, and you can always double check that you're getting the same value. So now we're going to take the derivative of both sides. And so on the left-hand side, we just have dx by dx, which is just equal to 1. And then on the right-hand side, we have d of sine of y by dx. But because sine of y is in terms of y, we do have to apply the chain rule here. So we differentiate d of sine y by dy, and then dy itself by dx. And this here is that derivative that we're looking for, which is y prime. So now we're going to isolate for y prime. So on my left-hand side, I have that 1, and then the derivative of sine of y is just cosine of y. And then there's that derivative again. So now solving for dy by dx, we get dy by dx is equal to 1 over cosine of y. So now here, I do have a simple enough expression that I actually will try to write it in terms of x, and how I'm going to do that is by using one of the properties of trig, which is the identity property. Knowing that cosine squared of y plus sine squared of y is equal to 1, then we can write that cosine of y is equal to 1 minus sine y squared. But sine y squared was our original function, which was x equals sine of y. So this part is x squared. And now the original derivative which we were looking for, which is y prime, is equal to dy by dx, which is 1 over cosine of y. And now in terms of x, it is equal to 1 over square root of 1 minus x squared. And that is our final answer. And now I hope you've seen that how implicit differentiation can really be helpful in solving implicit relations, derivatives of implicit relations, as well as just helping us figure out derivatives of certain complex functions, such as the polynomial rational function that we saw. And we do have some practice sets for this lesson, so make sure you are getting some practice with implicit differentiation and familiarizing yourself with the algorithm. And as always, if you have any questions, don't hesitate to reach out, and I'll see you all next class.